The 5th of March, 1979. 9 spacecraft, scattered across the solar system, are struck at the same instant by a pulse of gamma radiation so intense it saturates every detector built to measure it. For 0.2 of a second, the burst outshines every other source of gamma rays in the sky combined. Then, as suddenly as it appeared, it fades into a faint rhythmic pulse and falls silent. Nothing like it had ever been recorded. Ground stations cross-checked their instruments, certain something had malfunctioned. Nothing had. And it would take scientists nearly 2 decades to understand what they had just witnessed. The signal had come from 50,000 light-years away, from the wreckage of an ancient supernova in the constellation Dorado. A stellar corpse already catalogued, already considered understood. But no known object, no pulsar, no star, nothing yet catalogued could produce a burst that powerful, that fast, from a source that small. Whatever had erupted was compact enough to flicker in milliseconds, yet energetic enough to blind satellites across the solar system in the same instant. Some researchers at the time even wondered whether they were seeing something entirely outside known physics, a signature of new particle behavior, or an artifact of instrument error too consistent across too many independent spacecraft to dismiss. For 13 years, it remained unexplained, filed away as an anomaly, revisited occasionally, solved by no one. Then, in 1992, physicists Robert Duncan and Christopher Thompson proposed something radical, not a new kind of explosion, a new kind of star, a neutron star wrapped in a magnetic field 1,000 times stronger than anything else known to exist, powerful enough that its own crust could fracture under the strain. They called it a magnetar. The theory waited 6 more years for proof. In 1998, a second object, a magnetar named SGR 1900+14, erupted with such force that it compressed Earth's upper atmosphere from 50,000 light-years away, briefly disturbing radio communications on the night side of the planet. The 1979 event finally had an explanation. A new class of object, born from the deaths of massive stars, had entered our understanding of the cosmos, and it had been hiding in plain sight the entire time. Since then, astronomers have catalogued roughly 30 confirmed magnetars in our galaxy alone, out of well over 100 candidates awaiting confirmation. Some were first mistaken for ordinary pulsars steadily spinning neutron stars that flash like cosmic lighthouses, their beams sweeping past Earth with clockwork regularity. Others were classified as anomalous X-ray pulsars, objects that glowed far brighter in X-rays than their rotation could possibly explain. It would take years of overlapping observations to realize these were not 2 separate mysteries at all. They were the same phenomenon, caught at different moments in a magnetar's brief, violent life. A soft gamma repeater in one decade might quiet into an anomalous X-ray pulsar the next, its fury banked but never fully extinguished. In 2013, astronomers found one of the strangest examples yet. A magnetar named PSR J17452900, discovered in orbit just light months from Sagittarius A, the supermassive black hole at the center of our own galaxy. For the first time, scientists had a natural magnetic probe sitting almost in a black hole's own backyard, a way to study the extreme environment near the galactic center without ever sending an instrument there. Magnetars are born the way most neutron stars are born. The crushed, collapsed core of a star, many times the mass of our sun, compressed in the instant of a supernova into something almost incomprehensibly dense. But something different happens in the seconds after collapse. In an ordinary neutron star, the magnetic field is already extreme trillions of times stronger than anything on Earth. In a magnetar, something amplifies it further still. Rapid rotation and violent convection act like a dynamo inside the newborn star, wrapping and twisting the field until it reaches strengths that shouldn't be physically possible outside a handful of extreme scenarios in the early universe. The result is an object barely 20 kilometers across the size of a modest city, denser than anything else observable in the universe. A teaspoon of its material would outweigh a mountain. Its surface burns at nearly 10 million degrees. And it is wrapped in a field no laboratory on Earth could ever replicate, no matter how much energy was poured into trying. A magnetar's magnetic field can reach 100 trillion times the strength of Earth's own. To understand what a number like that actually means, imagine approaching one stage by stage. At 100,000 kilometers, roughly a quarter of the distance to the moon, onboard instruments would already begin to fail. Their navigation systems scrambled by a field stronger than anything they were built to withstand. At 10,000 kilometers, every magnetic storage device on a spacecraft would be wiped instantly, its data erased in a fraction of a second. At 1,000 kilometers, the field would be strong enough to erase every hard drive and credit card on an entire planet if the planet were unlucky enough to be that close. Closer still, it would begin to distort the atoms in your body, stretching electron orbitals into thin cylinders, rewriting the shape of matter itself, cell by cell, atom by atom, long before any conventional radiation could reach you. Long before you reach the surface, you would no longer be made of anything recognizable as flesh, not burned, not vaporized, simply unmade, at the most fundamental level physics allows. It's worth pausing on just how strange that is, compared to almost every other catastrophic scenario in astronomy. A star-going supernova kills with heat and blast force violent, but at least familiar in kind if not in scale. A black hole kills with gravity, stretching and compressing anything that strays too close. A magnetar kills by attacking the architecture of matter itself at a distance measured in thousands of kilometers, using nothing but an invisible field. There is no flash, no shock wave, no warning that most instruments would even register until it was already too late. The crust of a magnetar is not still. Under the relentless strain of its own field, it fractures a starquake, releasing more energy in a fraction of a second than the sun produces in 100,000 years. In December 2004, one such flare erupted from a magnetar called SGR 1806-20, roughly 50,000 light-years from Earth. In 0.2 of a second, less time than it takes to blink, it released more energy than the sun emits in 250,000 years. The burst crossed the galaxy and still struck Earth's atmosphere with enough force to be measured from orbit, briefly ionizing our upper atmosphere in broad daylight, and momentarily compressing the magnetosphere, the shield that protects the entire planet. Had it happened just 10 light-years away, instead of 50,000, the flare alone could have triggered a mass extinction, stripping away our ozone layer and bathing half the planet in lethal radiation within seconds, with no warning and no possible defense. To stand near a magnetar would not mean death by fire, the way it might near an ordinary star. It would mean the quiet, absolute failure of matter itself. Your body's chemistry undone at the atomic level, long before you ever felt the burn of radiation or the pull of gravity. There is no armor against it, no shielding material, no distance-based safety margin the way there is with heat or radiation in almost every other context in physics. No distance is fully safe. only progressively less catastrophic. Magnetars are rare, and mercifully, they don't stay dangerous forever. Astronomers believe only a few dozen may be active in our galaxy at any given time, their fields fading within roughly 10,000 years, a blink in cosmic terms. As the twisted magnetic structure gradually relaxes and the star settles into a quieter, more ordinary old age. But in that brief, violent life, they may explain some of the universe's deepest mysteries. Some giant flares are now suspected to be the source of fast radio bursts. Split-second pulses detected from galaxies billions of light-years away, some so powerful they briefly outshine an entire galaxy's worth of stars. In 2020, astronomers detected a fast radio burst originating from a magnetar inside our own galaxy. For the first time, a source named SGR 1935 plus 2154 caught by radio telescopes in the act of producing exactly the kind of signal that had puzzled astronomers for over a decade. New instruments are now being built specifically to catch these events as they happen. Observatories designed to watch the sky continuously, waiting for the next flare to arrive, ready to turn every available instrument toward it within seconds of detection. Some are ground-based radio arrays scanning wide patches of sky around the clock. Others are space telescopes designed to catch the first flicker of X-rays before a flare fully develops, giving researchers only moments to react before the burst fades again into the ordinary hum of the cosmos. Each one is a window into physics that cannot be recreated anywhere on Earth, a natural laboratory testing the limits of matter, gravity, and electromagnetism at their most extreme, in conditions no particle accelerator could ever approach. Somewhere in our galaxy, right now, a magnetar is cooling in the dark, invisible to the naked eye, unreachable by any spacecraft we could build, and utterly indifferent to anything it could unmake. If our own sun were somehow replaced by one, the story would end almost instantly. At the distance of Mercury, spacecraft electronics would fail outright. At the distance of Earth, the field would be strong enough to disrupt the planet's own magnetosphere entirely, stripping away the very shield that protects us from ordinary solar radiation, let alone anything close to a magnetar's own outbursts. It is, by every measure astronomers have, one of the least survivable objects the universe is capable of producing, and one of the rarest, tucked away at safe distances, doing its violent work in the dark, where nothing has to survive it. It is a relic of stellar death, and at the same time, a window into the deepest physics of the cosmos, a silent executioner, and a beacon into creation itself.